Section 1.11, Lines and Planes in Space, Part 2. Let's get started. Alright, so if you recall back in Algebra 1, you could find the intercepts of a line by plugging in zeros. Well, the same thing applies to when we want to find intercepts of a line that is in 3 dimensions. So if I want to find the x-intercept, I'm going to actually plug in the y and the z as 0. So I have 4x plus 6 times 0 minus 3 times 0 equals 12. Well, that's going to cancel out those. So I have 4x equals 12, divide by 4, and x is 3. So my x-intercept is 3, so I'm going to come to my graph and put an x-intercept at 3. Alright, then I'm going to do the same thing with my y-intercept. I'm not going to show all the steps because I know when I put in x is 0 and z is 0 that I will only be left with y, so I get 6y equals 12. Divide by 6 and I get y is 2. So on my y-axis I'm going to put a point on 2. Now remember, this is 3-dimensional graphing. If you need help with that, you can either K-mail me, call me, or that is actually section 1.08. Alright, and then the z-intercept, I would put in x is 0 and y is 0, so I'm left with negative 3z equals 12. Divide by negative 3 and I get that z is negative 4. So I put a point on negative 4. So notice I have points on both x, y, and z axis. If I connect my points like such, you can see the triangle that has developed. You can see the plane that has developed. That plane is the plane that intersects all 3 lines. So anytime we have 3 intercepts, we have a plane that's going to intersect all 3 lines. Now, I want to know what the equation for this line, and this line are. Well, for one, we have to name the lines. Alright, so it's pretty straightforward. These lines are all called trace lines. Okay, these are all called trace lines. Trace lines are drawn from intercepts. You have to have intercepts in order to draw a trace line. We're going to look at special cases in a second. This, from this point, intercept to this point, is the XZ trace line. The reason being is because it goes from x-intercept to z-intercept, or vice versa. This is the YZ intercept, trace line, YZ trace line, and then this one right here would be the XY trace line. So if I wanted to find the equation of the XY trace line, notice the only variable that they don't have in the XY trace line is the variable of z. So all you essentially have to do is take out the z. So that is 4x plus 6y equals 12. The reason being is because z is equal to 0. Okay, so z is equal to 0. So then if I do 3 times 0, that's 0. So that's why it's actually eliminated. So if I were to graph 4x plus 6y equals 12, I would get this xy trace line. So then the yz trace line, that would be eliminating the x variable, so that is just 6y minus 3z equals 12. And then the only one we haven't done is the xz trace line equation. The xz, the y is 0, so then that eliminates the 6y, so I have 4x minus 3z equals 12. Notice I have 3 lines in my picture, so I should have 3 equations, and I do. And this is, once again, this is the plane that intercepts all 3 axes. all three axes. All right, so this next page is going to talk about special cases. Now, in the previous plane, it formed a triangle because we had 3 trace lines. But what about planes that have fewer than 3 intercepts? So for example, this is the equation that's given. Okay, you notice right off the bat that there is a variable missing. There is a variable y missing. What that means is that this plane actually is never going to cross the y-axis. Think about it as an overpass. Okay, when you're going up the overpass and cars are going underneath you, okay, you actually never intersect with those cars. That's essentially what's happening. All right, so there is going to be an x-intercept at 3 though, and there also is an x-intercept, a z-intercept at 1. So we can still draw one trace line. Notice right here, okay? We still draw one trace line because there's still one that exists. A trace line is just a line drawn from intercepts, through intercepts, I should say. And then the equation of this line is actually still going to be the equation that was given because it does not have a y variable, so y is eliminated, and that's exactly this equation. Okay, so this is still going to be the plane that intersects the x and z axis. It just does not intercept the y axis. Okay, and then the last special case we have is when we actually have a plane that intersects only one axis. So for example, this is the equation that was given, z equals 4. So you can see the plane that intersects z equals 4. Here is z equals 4. So it has a z-intercept of 4. But it does not intersect the y or the x-axis at all. So we can't even draw trace lines because by definition, trace lines are only drawn through intercepts. And since I only have one intercept, I cannot draw a trace line. So the only thing I can do is say that there is one plane that intercepts this z-axis, and it is parallel to the xy plane. Alright, moving along, parametric equations. Alright, if you look at our table, okay, here we have x, here we have y, and here we have z. Now in our equations, really, they do not have anything in common. X is not based on y, y is not based on z, z is not based on x. They really have nothing in common, except for the fact that they all have t in common. Okay, they all share a common parameter, and that is t. When equations are uncommon to each other but common to one specific variable, those are called parametric equations. And we call the variable that they have in common the parameter. So t is our parameter. So you can see how all three are not in common with each other, but they all have the t in common. So I know what you're thinking. What in the world is that going to do? So if I look at this table, it's going to give us points to graph. So when t is 0, I plug in 0 for t. So 0 plus 1 is 1. Okay? I plug in 0 for t here. 2 times 0 is 0. And I plug in 0 for t here, and I get negative 2. So I can graph the point 1, 0, negative 2 on a 3-dimensional coordinate plane. And then I let t equal 1. So when t equals 1, 1 plus 1 is 2. 2 times 1 is 2. 3 times 1 is 3, minus 2 is 1. And now I have a point I can graph on my 3-dimensional plane. As t changes, I have points that I can graph on a plane. So this next figure does exactly that. So we just have these 4 points from the chart that we just saw on the last page. And then we graph those points. So this is the first point where x is 1, y is 0, and z is negative 2. and then second point, third point, and fourth point, and so on. So this line is the graph of the parametric equations of all of them together. Okay? It is graphed on a three-dimensional coordinate plane. This is used whenever particles are, when we do kind of distance time graphing, time of one, where is the particle here, here, and here type thing. And when I say particle, I'm just talking about an object. Hopefully you watched this video, because I know just in reading the lesson it can seem kind of a little strange. Hope to see you at the Class Connect session at 1. See you then. That should be a happy face. Bye.